Oh, g'day guys, Bennett here. Today I just want to go through the practice test for you. So, hopefully no force is equal to mass then just looking at the solution. So, if we go through the first one, the acceleration of that is falling due to gravity is 9.8 meters per second. That is in fact true, it's going downwards. So therefore, if we have mass to an object at rest with no inertia, that is false because we know that inertia is agility is something impulse force is defined as the heavy, it wants to stay where it is. Now, you might even really indicate where you pull these really important. We did look at two examples, tablecloth out from a right object. If something collides with an experiment, the dependent variable is the variable that generally is measured before and the after situation. That is true. So if you look at over here, you always fix the independent variable and the other one depends on that. So that's the one we do in meters per second. We repeat experiments many times to try and improve the reliability and accuracy of the initial momentum is true. And the basketball is going to be an object that's fired straight up in the air and has gravity acting once it reaches the top. So that's tenth of a second. If you think about gravity is the thing that actually slows the object down, otherwise it will keep going up and up and up forever. Now we know the change of momentum object is slowing down. As an velocity going in different direction. Okay, change of velocity means it's going to the direction or it's going down. Change of momentum is going to so they are initial momentum. I'm going to ask that sort of question again, just to test whether you get the concept. So that if we're throwing a basketball, let's go to question 2. Question 2 relates to a practical. Would say this you've got two cars going in your video, and after the collision, both the truck and the car are going to have. We're going to say part of the elastic collision. So an elastic collision means that the motion of two cars. So therefore, what would you say? Initial video number 1. Well, if you're going, you can see the gaps getting bigger. So therefore, that car is accelerating. Here, it's supposed to basically, obviously, use constant times, so that would actually work between the cars is that 3 seconds. And then we know the mass over here. So going down to part B, calculate the velocity of cars in 3 seconds going that way, right? So you can see the solutions down here. It's simply the distance they travel over the time period. It's obviously 2.2 of a second, right? So it's simply that using that velocity going that way. Right, calculate the average velocity of the cars over the 1 second. Coming to the initial momentum, you can also place them at the distance travel. So the way we do this mathematically is because so you go 10.9 metres in 1 second, and then go video number 1, you go 8 metres in 1 second. That will give you that value average. So therefore, this is going to do a very quick example of a bomb. This whole bit in here, for the bomb, you have that question. That is the trick. So state the law of inertia. It doesn't have to be word perfect. It's about the key concept. Is actually again what we said before. In a public setting, you do this one again. So, or you really do want to know. So, one object at rest, stays at rest, object in motion, stays in motion, travelling in the same direction, constant. Now, we know from Newton's second law, we could have worked that out. Obviously, that change in momentum, that only happens when that's in a 6 segment system. Obviously, the reactional force, reaction resistance. So, the law of inertia, we think about the force there, but we don't think about ideal worlds. But if we question 4, okay, so here's a question where you've got to use some information. So the speed of light is given to you 300,000 kilometres a second, momentum 3 by 10 meters per second. If we use time taken for it to reach there is 8 minutes, so that's obviously an SI unit, so you need to convert 8 minutes to seconds. This is actually so how far away is it? So this particular question is using the concept of velocity. If you throw a basketball at a wall, displacement over time, it will have we want to know the distance, so we've got to rearrange that using a triangle from the wall. So obviously, 8 minutes times 60 will give you 480 seconds. Today we want to go through that will give you 1.4 60 by 10 to the 11 metres. If we did this example, it would be okay to keep it in that particular. So you've never seen that video here. You want to go trucking ball, 4,000 high level, big wrecking ball, convert that to the truck station. So what massive chain on a big it doesn't ask you to give anything. So if you just go to first if this has got 0 what happens is when that ball hits the wall. Question 5, looking at Galileo standing at the top of the Leaning Tower pizza, throws the ball vertically. The momentum of speed of 10 metres per second. So at the same time, the system drops the force and an identical ball vertically downward at the speed of 0 metres per second. Which ball will have the greatest speed when it hits the ground? Now, just running through that, you've got to consider what's actually happening. So the ball's thrown upwards. Now, this is really a part of physics that you need to develop, which is you need to actually use one formula to develop another slightly different. We call that a derivation. Right. The reason why it's going to be slightly different is the one that Galileo throws up, it goes up at 10 metres per second, and when it returns to the original position where he dropped it, where he threw it up, it's actually going to be moving downwards at 10 metres. This is the other key concept. Right. So therefore, momentum means it's already going to be moving faster than the ball that's dropped. Right. So therefore, initial momentum, if it's already moving faster than the ball that's dropped, it will actually continue to accelerate minus initial rate, and therefore its velocity will get faster. What we know is by conservation, right? So the concept there about when it goes up and down, again when we're adding vectors, when it gets thrown up, tail, whatever speed gets thrown up, when it returns to the same height, it actually is going to have that speed downwards. We have a vector that goes here. That's the sort of thing you need to explain. In year 12, we'll extend that concept to reality. Question 6, a rocket's launched from nuclear. This is one where you can't use velocity equals displacement over time, because we're going to have a change in velocity. To work out what the force is, you need to know how long the ball. Obviously, what do we know here? We know the acceleration is the change in metres per second. Therefore, what's the velocity after the interaction through 35 seconds? Well, we know the initial velocity is 0. That works out to be. We want to find the final velocity. So it must be. You find that pretty easy. It is actually those formulas with velocity and acceleration, right? So I think you've got to come down here. The setting out is really what you need to see down the bottom of the screen. Again, make sure you capture label what you do know. 0, we know acceleration, no time, and then find out final velocity is going to be. So the formula you're going to use is v0 plus at. So therefore, it's going to go at 1820 metres per second, quite quick. So therefore, right. So that's the first part, part A. How high will the rocket go after 35 seconds? Again, obviously we need to know the displacement for that. Divided by 4,000. We know the initial velocity, we know the acceleration at the time. That's probably the one to use because you don't have to rely on the result from the previous section. So again, it's substituting to that formula there, where obviously 0 times by anything is going to be 0. It's simply going to be a half of the acceleration times by the time squared. Probably worthwhile, obviously not presenting that in metres, but going it to kilometres. Okay, so 31.85 kilometres is the height that you can get there. The graph below represents a velocity versus time graph of a car going around a racetrack. So consider that being. Okay, so we go through that process now. The one that you'll get in your test, and I'm expecting you to do, be something like that. The example is a racetrack, right? So what would we say about this? Well, example number 2 today is looking to do with what's actually happening there. Two cars. We've got a blue car and a red car. What's the velocity of the car? They've got different masses, 2 seconds speeds. Now, I've already reading the scale here, 10, 20, changing that 2, so the car's going 40 metres per second. You need to be working that same. At 7 seconds. Right, okay, so the car's going, I think if we think of the vectors now, you don't have to do it vectorially. I'm going to do it mathematically today for you. So going down to the next bit, this is what's the acceleration of the car? The initial momentum, the first 2 seconds, is equal to change in velocity over time. So what's the change in the velocity? Well, it goes from 20 up to 40, so it's changing its velocity by 20 metres per second, isn't it? So, so over 2, if we think about 2 seconds, so that's momentum 10 metres per second squared is equal to from 2 to 5. Well, we know it's not changing its velocity, so it's 0. You don't have to actually do any calculations for that. Just state it. From 5 to 7, well, it's changing its velocity by 10 metres per second over 2 seconds. So 12 metres per second squared times by 20. And then the last section, it's going from 50 down to 0, so it's changing its minus 50. So over 3 seconds, that works out to be negative 16.66 metres per second squared. Right. The area under the curve. Okay, if I'm going to work out the area under the curve, okay, I'm going to have to break this into some shapes. So what I probably would do if I was doing this I'll just show you the sort of shapes that I'll break it into. I'd probably be considering this one here as a newtons. Okay. What do we know about our situation over here? Well, we know that afterwards I've got this shape here. Has to be possibly final. So what are these big cars doing? They're going to do rear end collision, triangle, and then they're going to go off and combine speed. So if you wanted to, you could get rid of this one here. We know that I've got the following shapes. Is going to be I've got shape number mass of, and I would actually draw this on the diagram. 2 blue, 3 times by the velocity of the red. Okay, so then you've got 5 calculations to work out. So the area in this particular case, we know that this is 52,000. If you do that, then that will give you the area under the curve is in fact the area under the curve for a velocity versus time velocity is in fact the distance that's travelled. So therefore, that's really important to get that concept. So if I go back to my calculator, divide that by 2,000. You know you're going to get a question like that in the exam, in the test. And that right? It's either going to be a distance versus time graph, or it's going to be a velocity versus time graph for that. Okay, so if we go to the other questions for that, so that's what we answered there. 26. Describe in words what's happening in each segment of the graph. Okay, so we know what it is. We'll go back to the graph so you can see me talking through it. So you know it's starting off at 20 metres per second. Okay, it's moving to the right. Let's say if you were involved in actually accelerating at quite a rate of 10 metres per second squared, so that would then it's cruising along at 40 metres per second. Then it accelerates a bit more at 5 metres per second squared. Straight on 94 kilometres per hour. And then what it's doing, it's changing, it's turning around, and it's changing. So these cars are moving. So therefore, and accelerating means towards continuing to move off the original position at 6 minus because they're going in the same direction. It probably wouldn't be such a dangerous still accelerating as if it was a head-on collision. Actually, no, it's not. Remembering what we're doing here, if it's actually slowing down to the right, so it's slowing down at a speed at a rate of positive 16.6. If we have a car meters per second direction there. Until over after 10 seconds actually comes to a stationary stop. In this case, both of them are so this would be probably an example. Let's do another example where a car is. This is another example starting that you may at a particular speed and then finally recognise. If you've all played 8 or pool, so next question 8 goes to example where you're looking at and now what might velocity is. So therefore you've got to consider that as speed. One where you've got the stationary, not you can even do things like put spin on the ball, velocity equals displacement over time. We're saying there's no spin. Key thing here is again running in what information in SI units. So and the airplane landing on a runway with speed. So initial velocity is in fact 80 metres per second. The length of the runway is 1.4 kilometres, so that's 1,400 metres. What speed? And we want to see the deceleration of the plane. Will go off at. Okay, find the deceleration. If it slows in for me, the red ball is stationary, so a stop. So we obviously we know that the final velocity is going to be 0. Right, so we've got that initial momentum. So therefore, what do we know? Well, we don't know the time, so therefore you can't use any formula with the time in it. So you must use this 2as equals v squared take v0 really it's just the momentum of the white ball. Obviously to rearrange that you bring the 2a down the bottom line. And therefore you get a deceleration of negative 2.67 so what's the mass of the red ball of the white ball? Alright, so it's got 40 grams. The next part of that asks you how long does it take the plane to stop. Alright, so then you need to find a formula with, in fact, time in it. We know V0 and we know A, so therefore it's just a matter of now putting that into the formula, and you get 30 seconds. 0.04 kilograms. Question 9. My momentum of here. Sketch the graph showing the motion over here. So a hot air balloon rises at a constant rate of to a height of 3,000 metres in 60 seconds. That's going to mean that my initial momentum. So this is a height versus thing. So we know it gets to a height of 3,000 metres. So it's going at a constant rate, which means that it's going to be a straight line. I should give a direction. The next thing it says stays at the height for the next 100 seconds. So from 60 seconds to 160 seconds, it's going to be travelling at 3,000 metres. Okay, and then
You need to say that it's part of the
descends
question
back to the ground
momentum.
in 180 seconds at a constant rate. So 160 plus 180 is going to be 340.
You can write better
and it's
than I
coming
can.
down like
PI.
so that's
is
the
equal
sort
to
of motion
P5.
graph that you'd be expected to do.
So therefore,
obviously,
we know
the next part of that is
our
to
final
do
momentum,
not
P
just the
final,
displacement versus the thing. You need to do the velocity versus time graph. So therefore,
Now,
what's its
our
velocity
final
in the first
momentum
bit? Well,
in
it's a
this
constant
particular
rate. It
case
goes up
is
3,000
equal
metres
to
in
the
60 seconds.
momentum
So that
of
would be
the
50 metres per
white
second.
ball plus the momentum of
It's
the red
now
ball.
not changing its
Now,
height,
both
so
these
therefore
balls
it's
have
got
got the
zero,
same mass.
and then it comes down
so therefore,
to Earth
what I'm going to do in this
at
case
a
is
rate
just
of
work that out. So we know this is
3,000 metres in
0.4
180 seconds, which is minus
We know
16.6.
this is
7 metres per second.
0.04.
Alright, so I don't know how realistic
the
that is, but
velocity
you get the
of the
idea.
white ball. And that's
Question
gonna
10
be,
is a question about momentum.
0.4
Okay, so we've
times
been through
by
a
the
couple of these in the
velocity
video
of the red ball, which is
recently.
8.
So the before
Isn't it?
situation, the after
So
situation.
0.4
So if we start looking at the
is equal
momentum
to
of the cars and the truck or whatever
0.04
they are,
W.
you need to know the mass and
That
you need to know
times
the
by
velocity.
0.4 is gonna
Those
give me
velocities must be converted to metres per
0.32.
second. So obviously 100 kilometres per hour is 27.7
Right,
metres
so
per second.
therefore, I'm going to bring that
120
across,
is
so that's going to give me
33.3 metres per second.
take away.
Now again, my setting out is, I've done this on one page,
0.32
but you get what
is
I have to
gonna
do
be
there.
equal
To show my thinking.
0.04 V
Because the
W.
car, the
And so
900
therefore
kilogram
that's gonna
car
give
is
me
moving to the left,
0.08.
that's going to be a speed of minus 33.
And then I have to divide
So
that
therefore,
by
our overall
0.04,
momentum
and
now,
that'll give
obviously
me
it's
my
to the
velocity.
right because we've got a positive
So then
value.
I
If it was
divide
a
that
negative
by
value, it'd be that one to the
0.04.
left. Okay, we know that
That's gonna
afterwards
give me
these two
a
things are
value
going to
of
stick
2.
together.
So therefore,
Right, but we
the
know by
velocity of
conservation
my
law of
right
momentum
has
that
to
the
be
final
equal to
momentum has to be the initial
meters
momentum.
per second.
The only thing
And
that's
I
going
was
to change there is the
suspecting I was
mass of
gonna
the two
get that
things is
result
now going to
anyway,
be
because the only thing
2,100.
that's really
So
changing
to work out
here
the velocity,
is,
we
in
need
fact,
to
the
divide the
velocity.
final momentum
So if
by
it
the
goes
mass,
from 10
and
metres
that would
per
give us
second,
1.5.
I was
eight
thinking
metres
that
per
this
second
thing over
to the
here
right.
had to be 2
I
metres
probably
per
should
second.
convert that to
Conservation of momentum.
kilometres per
In
hour.
this
So you get a bit
particular
of an
case, we
idea.
would say that the
Times that by about
momentum
3.6 is going
is
to be a little bit
directly
less than 10
proportional
kilometres
to
per
the
hour.
velocity.
Okay,
because
what
the
did I
mass is
use?
actually not
Obviously, in
changing
this particular
in this
question,
particular case. And that's
I
a really
used the
important
concept
language
of
thing that you
law of
need to start
conservation of
working
momentum.
with here.
Right,
Mass
where
is
would the
constant,
energy be
so
lost in a situation like
say
this?
that
Well,
the
things like
momentum
heat,
is
sound,
directly
friction,
proportional
light,
to the velocity.
crumpling of the cars.
Now,
In terms of
all
what
I'm
I'm
expecting
expecting
you
you
to
to
do,
do,
would
I'm
need to
expecting
consider.
you to do
Alright?
any of these things
So
here
that's
with
pretty well much
the test. So our
objects
first
moving
test is
in a
gonna
straight
have
line.
those sort of questions
So
in it.
could be
You
stationary,
need to know
one
motion
moving,
graphs.
they could be both
either
moving in
displacement
opposite directions
versus
to each
time,
other,
or
they
the
could be
velocity
moving
versus
in the
time
same
graph.
direction
You need
as each
to
other.
understand
But,
how to
you know,
calculate
going
things with
through
constant
I've
velocity.
done, obviously there's 4 examples
Either
we've got
working
there
out
to
the
look at.
velocity,
So the
displacement,
key
or time,
steps are for
and then
doing
you need to
these
obviously
is,
use those other laws,
working out the initial momentum,
to
which is
be
the
able to
addition
work
of the
out
two objects.
second step is to make sure that
acceleration
you
is
can
going to be, what the
conservation
displacement's
of
going to be, what
momentum.
the final initial
The
velocity
third
is going
step
to be,
is to actually
find
the
considering a
unknown
different
by
scenario using the formula.
Alright, so
Have a go at these
and
questions.
obviously I'm
If you
going
have
to
some
put
trouble,
something in
make
here
sure
about
you
some of the
catch up
prep
with
work
me
that
in
you've been
class.
doing as well to test whether you understand the concepts of what we're doing with constant motion or acceleration. Alright, so hope this helps you. Make sure that you work through that practice test to make sure you have a go at doing all those questions, and catch up with either myself or someone else if you need some help.